Hello and good morning, everyone. Welcome to today's webinar hosted by AAC Kalkitech. I'm Midun from the marketing team at AAC Kalkitech, leaders in grid communication solutions. So today we are going to discuss about something that has caught a lot of interest lately, VPRs or virtual protection relays. This webinar will explain the VPR concept, an architecture where software-defined and virtualized platforms are deployed to host the critical circuit protection functions for an advanced and agile grid. So we will dive into the key concepts, what's the need for VPRs, and it'll explain some of the use cases as well. A couple of hygiene points before we start off this webinar. This is going to be a 45-minute session and will be followed by a 5 to 10 minute Q&A. Please note that this is a listen-only webinar. If you'd like to ask any question or have any query, please feel free to put that in the chat screen. I will consolidate all the questions and have it answered towards the end of this session. If in case we are not able to answer every question, we will definitely get in touch with you personally and try to address all other queries. Of course, a recording of this webinar will be automatically sent to all attendees, say around 48 hours after the session. We will also be emailing you a webinar participation e-certificate in a separate mail. All right, I see quite a few people have joined in. Uh, Great. So let me now introduce the host for today's session, Rupesh Arya, who is the AVP, the Digitalization and Virtualization COE team at AC Kalkitech. Rupesh has almost 20 years of experience in the power and utilities industry, specializing in developing and implementing innovative solutions for grid modernization. He is actively involved in initiatives focused on VPAC, DER, AMI 2.0 metering, and grid AI. He is currently an active contributor to the E4S and VPAC alliances and is leading the E4S software working group. All right, so without further ado, I'm handing over to Rupesh. Hey, Rupesh.
Yeah, thank you, Mithun. Hello, everyone. Good morning, good afternoon, depending on where you are attending this webinar from. And thank you for taking time out from your schedules to attend this webinar. So let me just go through. I'm just trying to give an overview of the virtual protection relay, not really into the detailed one, but yeah, I'll try to cover and maximum the basic introduction of the virtualized platform. Okay, so brief about the Calcutech VPR initiative. So Calcutech is primarily a communication technology company. As a technology company in energy and utility domain, Calcutech is committed to innovation in grid modernization and is actively involved in these virtualized protection, automation, and control R&D activities. We prefer to work along with OEMs, utilities, and SIs in developing software-defined solutions for the PAC platform. Calcutta is actively participating in the VPAC Alliance, and which is a coalition of utilities and industry partners with a common desire to have a standard-based secure software-defined architecture to host PAC solutions for the power system substations. Leveraging on Calcuttech's experience in developing VPR reference application, Calcutta has set up a lab for helping OEMs and utilities in adopting VPR. And the lab infrastructure can be availed as a services by OEMs, utilities, system integrators, and EPCs, and by any VPAC stakeholders. Uh, yeah, so with that, I just start with the VPR details. So the section will talk about the need for VPR. So we'll start with the evolution of protection relays. So if you look at, we have this, very old protection relays. Maybe we can say that it's from the start of um, the commercial use of electricity. We started to identify and isolate the faults, and that effort was always there to have an efficient protected grid. So so this started with the electromechanical relays, where the relays were completely dependent on the pure electromechanical system. So basically, you will be having an induction disk which will generate a torque against a magnetic torque. Let me just put on my, yeah, a magnetic torque against, and there will be spring adjustments that introduce some sort of protection isolating the fault. So again, this was completely based on pure electromechanical equations. Then we had a solid state relays where there is no moving parts, which came in the advent of electronic circuits and transistors. And there was no static or no moving parts with in comparison with electromechanical relays. But overall, some of the principal functioning was somewhere similar to the previous one, but it had better precision than the electromechanical relays, with the mechanical parts completely replaced by the electronic components there. Then we had the more digital relays with all the microcontrollers. It has a way of programming where we can create small programs that can run in a microcontroller. They had a minimal but some communication interfaces as well. So then we had the current intelligent electronic devices, what we call now as the IEDs, which are based on high performance microprocessors and DSP systems. These IEDs, they can support multiple protection functions within the same device, and they of course have efficient communication interfaces. So most of the IEDs, they are based on real-time operating systems. Um, so with that, the question arises: so what will be the next item with all these current system here? So what is the next in the progressive evolution of these protection relays? So answer is the VPR. So virtual protection relaying is considered as a potential candidate that can take the protection relaying to the next evolutionary stage. So virtual protection relay, it's basically an approach to decouple relay software from the dedicated hardware, leveraging the IEC 690 standard and also the advanced virtualization technology that we have now. So virtual protection relay, we call that uh, VPR from now onwards. So VPR will ensure meeting all the existing characteristics of a relay, but with greater flexibility, portability, resilience, and interoperability. That will be the aim of the VPR. So VPR system can fit into any existing workflows, standards, or protocols, and shall have seamless integration with existing system and devices. It can execute all protection schemes that are using IEC 690 sample values and queues. So the IEC 650 standard is a must for the implementation of VPR. So uh, yeah, we have some slides coming up, which is indicating the IEC 650 substation diagram, where we have multiple IEDs are deployed and how that is converted to an virtualized platform. So what is the need for the VPR? The slide basically, just lists some of the, uh, deficiencies what we have in the existing system. So if you look at a single um, medium voltage substation that may require 100 individual IEDs, and hence high operational and deployment costs will be attributed to that because of the lot of complex wiring and high maintenance and large number of infrastructure and the utilization of the real estate. So um, so what we are trying to do is to see how a VPR can really, sort out all these issues which we are currently, facing. So if you look at, there are devices, all the current IEDs, they all have the hardware and software bound together, resulting in very obsolescence and feature upgrade risk and cost. So a utility often need to procure a different relay of protection schemes that require maintaining and getting trained in multiple vendor dependent hardware and software tools. So the cost involved in relay commissioning, operation and cabling adds to the more to the total operation cost. Again, it takes more time to test, develop both the hardware and the software. And there is this important aspect of the cybersecurity. So all the complex upgrade cycles of the existing system and the cybersecurity updates all are very difficult to carry out in the conventional system what we have now. And also the last one where we have the DER systems. So integrating existing relays to a new grid with high penetration of DER devices pose more challenges, which demands more innovations and implementation of custom control functions. These all attribute to the need for a virtual protection relay system. So I'll just explain about the key drivers for the VPR that has happened, and then that is also, causing for the implementation of VPR. So the main key driver for the VPR is the technology advancements what we have, part of the digital transformation happening and the grid modernization happening. So VPR systems basically benefit from all these digital transformation, all the improvements in the visualization technology we have, enabling efficient allocation of resources based on the visualization platforms and enhanced flexibility in the deployment. That is the main advantage of the visualization platform. And also with all these increased processing capability, with all the new gen server hardwares, these relays can handle complex algorithms and tasks with higher speed and accuracy, and at the most ensuring the reliable protection for the electrical systems. So there are hardware designed to withstand harsh substation conditions, which are compliant to the IEC 620-3 standard, and is accessible for use in the virtual protection relay systems currently. And the digitalization of the substations, that stands as a pivotal factor for driving the adoption of VPR. So enabling real-time monitoring, control, and enhanced system intelligence for efficient electrical network management. So it is essential to reduce the maintenance requirements, ensuring devices work better for longer periods, minimizing the breakdowns, and making the maintenance process more straightforward and cost effective. And always cost effective is the key word here. So another driver for adapting VPR is that the it decreases the expenses by recurring less hardware and maintenance costs, thereby enhancing the overall affordability by the utilities. And then the implementation of redundant networks, and also the different redundancy technologies offered by the virtualization platform, and the concept of the digital twine. So all these avoid the challenges with the single point of failures happening in the grid. Since the relays is IEC 650 compatible, so it gives seamless integration with any existing industry standards and protocols. So with that, I'll move to the VPR concepts. So for that, let's quickly see the protection workflow, what we typically see in a substation. So here you can see um, a typical substation where we have the currents and voltages, which is measured by the CTs and PTs. That basically gives all the current and voltage signal measurements from the field, and they are wired to a typical numerical protection relay where the currents and voltages will be continuously monitored, and whenever it identifies a fault in a section of your grid, so it will take a corrective action, normally in the form of a trip command that will be issued to a circuit breaker, which will try to isolate the fault from the network. Yeah. So yeah, so this is a typical operation protection flow where we have these numerical relays. They'll be having some additional interfaces where you can have a local SCADA that um, connected to, which will give you the real-time information, and also the real-time information will be fed to a remote control center through a gateway. So this is a very simplified protection relay approach that is there in a substation. In a typical substation, there will be multiple bays of circuit that require more than 100 such numerical relays. And typically you will see multiple devices provided by multiple vendors. And all these will be maintained by multiple protection engineers, and each of these numerical relays, they'll be having their own configuration tools, which will add more complexity in the relay configuration management. So I'm just moving to a IEC 650 based substation. Now we can here also we can see a similar workflow where we have the CTs and PTs in the field, which will sense the current and voltage. There will be an MU or a PIU that does the ADC conversion and provide the detailed data to the process bus. The data will be received by the multiple protection equipments, and each of these IEDs, they'll be collecting the real-time samples from the process bus, and they'll be running the protection algorithms inside the IEDs, and whenever there is a fault, they generate trips or the corrective actions, and that will be transmitted to a through a goose messages. And also we have the standard IEC 620 client applications like the SCADA or the gateways or those things that connected to the station bus. But you can see that here there is a big difference from the previous workflow with the numerical relay, that these IDs, these are not physically connected to the CTs and PTs. Instead, we have a bus concept, and this is something specific to the IEC 650 substations. So as you all know, IEC 650 provides an interoperable framework for substation protection, control, and monitoring. So it's a protocol that defines the data exchange, also defines or provides specific profiles and services, specific services and different profiles, and no definitions, and also a structured naming convention for the device data. So even if you have IDs provided by multiple vendors, um, so since we follow a common data modeling there, the devices will talk in a common language, and the data will be represented in a common format, which aids in the interoperability. And on top of that, IEC 600 defines an standard configuration language. That means a common tool can create the configuration for multiple devices, no matter they're even if they're coming from multiple different vendors. Still, all these devices will be able to understand a common configuration. And another feature of the IEC unit is that they have the standard device conformance testing, which will ensure that multiple devices from multiple vendors will work interoperably. So these are few highlights of IEC unity that is beneficial, and that is benefiting um, the complete IEC unity standard. And so we'll just quickly go through the process bus part of the IEC 620 standard. So about the process bus, it allows connection between the protection, measurement, and control IDs and the private shared equipments. So IEC 620 allows all sensor measurements to be available simultaneously to all controllers in the network. So there are MUs which are used to digitize the measurements and publish them to the process bus. So we have very well defined specification that clearly says how this data transmission happen, and how merging units are used to publish them to the process bus. So here we talk about the Goose. So Goose is the abbreviation for the generic object-oriented subsession event. So these are high-speed data exchanges that are used for communicating directly between the IDs. So if an IED wants to send something to another IED, it can use a Goose message. Similarly, a trip message can be sent as a Goose message to the field. So IEDs can publish this Goose message for other IEDs, and also can subscribe the Goose messages from other IEDs. So they can. So the key point is, we do not have any copper connections coming from the field to the device. So all of them are subscribing, publishing to a communication bus. So Goose also has a periodic retransmission that are happening to ensure the messages are not missed. So here we have a protection workflow um, in the scenarios where we have the samples of the current and voltages received the emerging unit values, and the protection function continuously analyze the samples to the identify running in a server hardware or something like this. So multiple virtual protection relays can be running here, and so whenever it VPR identifies an abnormality, it sends a trip command on the to the field. So upon the fault detection, so the circuit breaker in the field isolates the line on receipt of a trip command based on the electromechanical operation in the. So this is a, a protection workflow simplified in an VPR environment. So we have a 115 kV, 13.8 kV subsession SLD shown in the right side with multiple circuits. We have 102 incoming feeders and 506 outgoing feeders there. And so typically this will have multiple physical protection relays. But here all these are represented by this Dell server, which I was shown in the diagram. So it is Dell. It can be any Intel Xeon server hardware um, that is installed with all these. So
Hello, hi, Rupesh. We are unable to hear you. Hello, Rupesh.
Can you hear me?
Yes, yes, Rupesh. Yeah, now we can.
All right, thank you. Yes. So we have this a big SLD shown here. So we have 5 or 6 incoming feeders and there is 15 or 16 outgoing feeders. Typically, this will have around 50 or more protection IEDs. So all these are currently shown as a set of virtual protection relays running in a server hardware. So the system will be very simplified as like this. So all the protection relays will be just represented in this server hardware. So the transition to a VPR um, based substation will look something like this. So we have the substation control room that's shown on the left side, and we have different IEDs and different other firewall or security or other devices also here shown. So all these can be represented or can be encapsulated to an rugged server as shown in the right side. So the control room will something look something like this. So all the 50 or 100 the protection IDs will be represented in this fashion. Yeah. So here I'm just showing the transition from an the current IC600 based substation where we have physical protection relays to an virtualized system. So where we represent all the physical IDs in just one box. So here we'll talk about the virtualization, how it is. How is the definition of virtualization? How that can be used for the VPR. So uh, virtualization basically uses software to create an abstraction layer over the computer hardware. So this software abstraction layer allows the hardware elements of a single computer to be divided into multiple virtual computers, as you can see in the right side. So this is one server computer that has multiple virtual machines shown. So these VMs have their own processors, memory storage, and operate as distinct computers. So each VM operates with its own individual OS, mimicking independent computer systems. So virtualization allows the efficient utilization of the computer resources. So when we allocate an CPU core or the memory storage to one particular VM, which will not be allowed for another VM. So in that sense, we can clearly encapsulate the resources for one VM and make sure that the applications or the services inside that VM uses the complete resources allocated for it. So benefits of virtualization. So here are the some benefits I have listed here. So VPR basically simplify and unify the methods of commissioning, maintaining, monitoring, upgrading, and the replacement of the protection relays. So because it's all our software defined systems now. It is expected to have considerable effort reduction in design, construction, during the installation and commissioning of the protection systems. So the labor of maintenance and the upgrade will also be very much reduced. This will be a big leap towards the unmanning of the substations as well. So IC 600 substation has already moved from the analog copper wires to the communication cables, and now this mainly uses the fiber optic cables. So so in an virtualized environment, there is no physical IDs, and all are software defined systems. Hence, there will not be any physical cable connections required between the IEDs. So there will be only few cable connections between the physical servers. So fewer cable connections and terminations means fewer materials, length, less cost. And it also ensures a safer physical edge environment compared to the older copper wire based systems. So virtualizing mechanism provides an advanced redundancy techniques which are already proven in the other sectors of the digitalization. And there is a main advantage of VPR, that is the multi-vendor compatibility and the interoperability, because since our all are software defined systems, so a single server hardware can include the software defined systems from different vendors. So central management of IEDs and VPR orchestration is one of the main benefit of the virtualized environment. So virtualized systems provide many services that can be leveraged for a centralized device management, from where IDs can be deployed, configured, managed, and monitored centrally. The same can be used for analysis of the faults based on disturbance records collected from different IDs. And also, there can be proactive fault detection systems that can be installed over the central device management systems. So here we are just showing one IED model as a VM. So if you look at, there are um, different protection functions and different modules that are encapsulated into one virtual machine. So this will act as one virtual protection relay, and we have another VM that works as in the second virtual protection relay. So all are running as multiple virtual machines over an virtual machine hypervisor. So there are newer options for redundancy here. So we can have redundancy active virtually, or active physically. So multiple instances of protection and control applications can run together and in different virtual machines or different virtual servers without, ensuring there is no single point of failure there. So we'll just go to the VPR implementation. I will just give an example of a VPR reference implementation to get an idea how this can be implemented, how this is being implemented. So this is an IEC 70 VPR framework overview, which Calcutta has. So this we used for developing a VPR reference application, which we did sometime back in 2019, mainly for evaluating the virtual protection relay and to prove that virtual protection relay can ensure or give better result than the conventional protection relays. So this VPR framework had the an VPR infrastructure based on the IEC 650. It had has this IEC 600 sample value subscriber conditioning module, 600 server disturbance recording, and SCL configuration modules. And all these are exposed as inter-process APIs that can be used for by other vendors or other applications that are using the 650. So we use this VPR framework for creating the VPR reference application. So highlights of the VPR framework is that it has the um, basic framework that can be used as a backbone for implementing protection relays and different IEC 600 tools. It has many mandatory communication modules uh, which are as per the IEC 600 standard. and it has the very robust IPS that can be implemented and integrated with the protection algorithms. So with this, we also provide the reference VPR, which we use for evaluating the VPAC platform. So these are the different modules that we have the all the IEC 620 services that is required, and also we have the disturbance recording module and a reference signal conditioning module, and we had many reference implementations of protection functions as well. We had distance protection, transformer differential, and many variants of overcurrent protection and breaker failure protection. So these are reference implementation. These are not really for implementing as an not for an production environment, but more for an evaluation per se, and for accelerating the VPR development of the OEMs. So this is the VPR implementation, conceptual implementation, which we also developed as the reference for the evaluations and no, performance benchmarking of the VPAC platform. So this is an overall architecture where you see on the top of the framework, uh, this is having um, the VPR infrastructure or the VPR framework as the backbone, implementing the IEC 620 substation based protection relay. So it has all the IEC 620 essential modules like the sample value subscriber, the goose publish subscribe modules, and reference disturbance recording module as well as an MMS server implementation. So as we start from the left side, so we have these CTs and PTs connected to an merging unit. Sample values are published to an process bus. So in the center, we have a VM hypervisor that is running an server hardware, and the server hardware has this virtual machine hypervisor running on it. So the reference VPR application runs inside this VM that is over the hypervisor. So here, if you see, there are um, uh, different protection reference functions running. So there is this signal condition module which receives the process sample values, and it is provided to these protection functions as an in the process API data, and these protection functions runs the protection logic, and whenever there is an abnormality occurs, it sends the goose message through the MMS module here to the process bus, where a PC or a PAU takes the decision of operating the circuit breaker. So there is this MMS server that does all the goose publishing and subscriber components, and there are IEC 620 configuration module that does all the SCD file handling, which has all the IEC 620 configuration for the VPR here. And we can have additional 620 client modules that can be connected to the MMS server here. And this VPR application, reference application, comes with a web HMI that can be used for configuring the VPR. So this is almost in line with the many protection relay implementations. Um, so basically, so we followed the same method, and so that we can evaluate the platform for OEMs and ODMs and utilities. So I'm just giving an excerpt from the evaluation test results. I just took one set of test results, which is published sometime back, and even in fact, it is part of some of our white papers as well. Here, the reference VPR was used, and which is running on a VMware ESXi hypervisor based on Intel Xeon based server hardware. So we had an Photon OS. And with one CPU core and 4 GB RAM. So we could verify that the protection function sends the trip signals upon the detection of a fault, and the trip go signal were received with a time span of 1 to 1.5 cycles of a power signal. So the so this what it says is that we are getting a good result there. Uh, so if you look at the on the right side, we have another set of tests conducted based on that. We have plotted a graph here showing the response time versus the fault magnitude for the instantaneous over current protection, that is the 50 protection function. So these tests were conducted on a VPR with this configuration, and so graph shows a data that starts with a 5 ampere as the threshold current, and the pre-fault current was 4 ampere. The fault current is increased to several multiples to the threshold of the current, and the response time was basically recorded for against each test cases. So as expected, the response time decreases with the increase in the fault magnitude. So overall, the observation is that consistent performance of the protection function was found with very multiple test case iterations, where a faster response time was seen with the fault current magnitude when was increased. So these are the VPI configuration tool we used, the SCL manager tool from Calcitech for the SCL configuration tool that created the SCD files for the virtual protection relay. And we had the protection function settings configuration from an WebHMI, which is used for configuring the VPR reference application. And we had a dashboard where it was showing all the status of the functions, and it also had the phasor diagrams and the processed signal conditioner data also shown. Yeah, so here are the expected benefits. So we have the simplified and unified methods of commissioning and maintaining, monitoring, and upgrading of replacing the relays. So all these are very simplified in the software-defined systems, and also we have very reduced design and construction efforts during the installation compared to the physical relays, and we have reduced maintenance and upgrade labor, and reduced cabling and terminations, and few dangerous connections in the field, and improved redundancy, multi-vendor compatibility, and interoperability. Yeah, so we can extend the same workload with as we did it for the protection relays. So same software defined system we can extend to other areas like the asset health management, analytics systems, advanced restoration schemes, or fault classification and signature analysis systems, advanced ADMS systems, metering and settlement. All these can be moved to a software defined systems in the same way. Yeah, so this is the Calcitech Advanced Grid Automation Technology Lab we have in California, so in Santa Clara. So where this is mainly a joint investment with Intel and ASC Calcitech. So and we have a collaboration with the Santa Clara University to do many of the R&D activities in the lab. The photos shown in the picture are from the actual lab. So the goals and objectives of the lab was mainly to promote the virtual protection relay and develop VPR pilot projects. So and also making the availability of newer Intel server processors and different ODM hardwares, OEM algorithms, and other software systems which is confined to the virtual protection relay in the lab for the industry to evaluate and do the performance benchmarking. So what's in it for the stakeholders, mainly from the VPAC lab? If you look at for the utilities, it is mainly the training. They can understand and explore the test bed, how the VPAC is tested. They can build their own custom environment in the lab and validate the performance, then deploy into the utility lab, then run the pilot systems and do performance benchmarking. And also know they can do the all the knowledge sharing in the industry and build expertise over that. And similar for ODMs and OEMs, they can use a lab to integrate with other hardware and use the visualization platforms, use the VPR algorithms from Calcitech and also from the commercial virtual protection relays like the ABB SSC 600 and other tools in the lab, and basically benchmark their system, the ODMs and OEM systems, that includes all the switches and other hardwares used in the pack platform. And also system indicators can get trained and they can use the system for testing and deployment experience. And the last point is the it's big visibility to the OEMs and ODMs and system integrators when the utility customers visit. The utility customers will be given with live demonstrations on the VPR system. So the lab provides many structured programs and services. So it provides application services that includes the VPR reference application and VPR development framework and the IC620 development framework for developing different uh, products, IC620 tools there. And the lab has the different services like the substation modeling. We do substation modeling with respect to the virtualized world and compare it with an existing physical protection relay based substations. We also give the test bed and pre testing for newer substation implementation, like for the data centers and collector substations, for the experience of the VPR based protection system. We do HAL testing using RTDS and many performance interoperability analysis for protection relay vendors and different hardwares. And there are engineering services. This is connected to the Calcitech services division as well, where we do some of the transition from fixed function hardware to the software defined systems, like how we did for the virtual protection relay. And also we do some of the grid analytics using AML on our own, and also we have a few tie-ups and discussions going on with the um companies in this domain. And also we do many VPAC and IEC 620 engineering services as well. And the training and hands-on, that is the main one of the main objective here. And also we do lab tour and demonstrations for utilities and OEMs, mainly to give an overview of virtual protection relaying and also to understand how the lab infrastructure, lab services can be used for the evaluation of the VPR. And also we conduct live demonstrations of the VPR to get the confidence for the stakeholders. And last, we provide the lab as a service as well as a subscription for OEMs, ODMs, SIs, and EPCs. Yeah, so we have VPAC Alliance. So basically, so this basically I was talking in the beginning. So this is mainly for defining a future of the grid, leveraging all the virtualized protection, automation, and control. So Alliance aims to accelerate the creation of a standard-based, open, interoperable, and secure software-defined architecture to host the protection, automation, and control solutions for the power system substations. So there are many OEMs, ODMs, utilities are involved in this. So, so if I give some instances, we have SE, SRP, Avangrid, many utilities, and the OEMs like ABB, Schneider, GE. and many other OEMs are part of the alliance. I have a slide coming up with showing the alliance members. So, so about the alliance overview, so if we can say that this is a system or an alliance mainly for mainly for the coalition of utilities and industry partners and other stakeholders who are having a common desire to drive a standard-based software-defined architecture to host the park solutions for the substation. So we have currently the Brand Heap Director, Protection Automation Control of SRP Utility in Arizona. He is chairing the VPAC. Um, so the alliance will be actively working towards the documenting the specifications for a unified edge for substations and utilize existing standards and collaborate with standard organizations like the IEC and also promote market adoption and support market transformation. So these are the VPAC alliance members. So we have ABB, Schneider and GE, those relay OEMs, and we have the hardware companies like Advantech and others. And also we have utilities, as you see, Alliander, Avangrid, Southern California Edison, Tower Energy, PG&E, and recently RTE has joined the alliance from France. And we have many virtualization platform and software platform vendors like VMware, uh, Red Hat, also a part of the alliance. Yeah, so we have these training and hands-on sessions part of the lab, mainly covering in-person and online training courses, and there are hands-on and sessions with the industry-leading test sets and simulation platforms available in the lab. And we also do the performance testing and demonstrations in the lab, and also walk through with all the virtualization platform supported hardware in the lab. And there are many programs, training programs like the in-person training 2-day programs and the in-person training 5-day programs that cover many aspects of the IEC 650 and virtualization platform. Um, and there are many online training sessions as well conducted part of the this VPAC initiative from Calcitech. So there is an in-person training schedule that is dated for March 18th and 19th, 2025. This is just 1 week before the Distributech event in Texas. So we have this venue at Santa Clara where we have our lab located near to the AC office. So yeah, just wanted to inform you about the training program as well. Yeah, so with that, I just covered the webinar presentation. Thank you. Over to you, Midun.
Hey, thank you so much, Rupesh, for this informative session. I know there are a lot of points that we can go deep, but I mean, considering that we have 1 hour, it's great that you have been able to cover most of the major aspects. Yes, so we have a few questions from the audience. All right, so one is there any commercially available virtual protection relay available on the market?
Yeah. Yes. Uh, so many of the OEMs are currently working on their VPR development. So last year, ABB has released its virtual protection relay, which is named as SSE 600 SW, which is mainly derived from their own central protection system with the name SSE 600. So and so they are very actively having virtual machines, tested on different visualization platforms, and they have the different versions already available in their website. Recently they have released an version 1.5 in December, and many OEMs like GE, Schneider Electric, and many others are working on their development, and soon they'll be showcasing and releasing their VPA versions as well.
All right,
Yep.
all right, great. Another question is there any virtual protection relay commissioned running in any rail substations?
Um, this is not yet, but there are many evaluations that has been happening from last 5 years, and currently there are many utilities who are running VPR pilot projects. So soon we can see more RFPs going for a pilot, and soon we'll be having few. Yes.
Sorry, Rupesh, again, we are losing a bit on the voice, but yeah, I think it's slightly better now. Right? Yeah, so we'll just go on to the next question. We only have a few minutes. So, how is the critical timing of protection relays achieved in the virtualization environment?
Okay, so if you compare the older relays, so mainly they were running on microprocessors, and no, even the auto systems were using like less than 1 gigahertz, like 300 megahertz or 500 megahertz systems, processing systems, and very less memory. Or, memory were available in those relays. So currently we have very high processing capability uh, uh, from processing capability with the server hardwares. For example, the Intel Xeon server has technology there. They have the TCC and other configurations that ensure very high performance execution of services. And over the top, there are these hypervisors, like the Type 1 hypervisor or the bare metal hypervisor or the base KVM based hypervisors that ensure real-time performance with there are many performance settings like the CPU core pinning and other performance fine tuning like the VT settings, etc. That is available both server and the hypervisor platform. So this is in association real-time flavored operating system running over that can clearly meet this critical timing.
All right,
In fact, yeah, so we have many results which we already did, and so that has proven that it's possible. Yes.
great. Uh, we have few more number questions, but very less time. But we'll try to answer all of them. Else, we'll address you individually through email. So one is with regards to uh, legal aspects. So if you have, in case of a failure, third-party vendors can blame hardware, software, VPRs, and not their software of protection function. So is that going to be an issue?
Can you repeat the question?
So in case of a failure, would the third-party vendors be blamed, or
Mhm.
can the third-party vendors blame the hardware, software, or VPRs and not their software of protection functions?
Yeah. So here we have a clear, layers. If you look at, there are virtualization there. There are the base hardware layer. Over that, we have the operating system layer. And if the virtual protection release is implemented as a Docker container, then the container layer will come. So all these layer has a definite configurations and different logs there. So, and these logs as part of, if you look at part of the VPAC alliance, we are clearly defining how that needs to be used for the auditing and for any quick reference there. So there'll not be any question of no, I mean the blaming there, so it will be all evident there. Yeah.
All right. Next is any specific cybersecurity concerns with VPRs? Anything that we have to be mindful of? Or what's been done there?
um, yeah, so with when we move to more software systems, yeah, so there is an we may have more cybersecurity challenges as well. But if you look at the existing systems, so many of the existing systems are running um, without any cybersecurity updates in the system. So there are we know many incidents happening across the world for the, and it is been increasing such attacks in the world. So if you look at the platform like VPR, where there are clearly defined cybersecurity standards, that is that includes the hardware and software, which make the hardware both very hardened. And there are many standards like the IC 670, the 1613, and the NESIP standards and other standards are followed to ensure a very secure system for the VPR, which we couldn't do for the existing substation systems.
All right. Okay.
And so just to add that, so part of the VPAC Alliance, we have an cybersecurity specification working group. So where we are basically defining all the uh, cybersecurity guidelines for the VPAC system, making it proof. I mean, secure for the all the attacks. Yeah.
Right. Yeah, I think this is something maybe related to what you have been discussing also. Like, what are the efforts that we made to standardize the VPR to something like maybe say IEEE standard or something like that?
Yeah, so there are working groups. Part of the TC57, there is a discussion. There is a working group happening there, and outside that we have the VPAC Alliance, where we are defining, and recently the even for the conformance test. I mean, the VPR is currently, I mean, added to the test cases. So yeah, so basically, it's being, there are standards coming up for the VPR as well. I
Great.
can
Okay.
share, yeah, some of the details in email as well.
Perfect. Yeah. Can this VPS solution be implemented for a part of an IEC 6950 based substation and then migrate remaining base over a period of time?
Yes, this can be done. Uh, because we are using the IEC 600 standard there. So all relays that comply to the standard will be interoperable. So we can run an physical protection relay along with an virtual protection relay in the same substation, provided that it's an IEC 600 detail substation.
Got it. Are there any demo or trial versions that a utility can install and test run, whether we can simulate?
Yes, yes, there are. To start with, Calcutta itself has an VPR reference application that can be used for the evaluation, and also there is ABB SSC 600 product already available in the market. Yeah, that can be used for running evaluations and pilot. In fact, Calcutta is working with utilities for evaluating the VPAC platform, and also helping them in setting up VPAC lab.
All right. Okay. This is it to the US alone or is it across? other geographies
Uh,
as well.
eh, yeah, other geographies as well.
All right, that's great. All right. Okay, question regards to reliability. If the VPR panel power supply fails, or the OS or the operating system fails, how will it impact the ID, overall ID system protection?
Yeah, so all these server hardware comes with the redundant power supplies to say to start with. But otherwise, if the failure is it's similar to the physical protection relay itself, like I mean the power supply. Uh, but having said that, there are many levels of redundancy that we can do over the system. Like we can have the active and backup systems, primary and backup protection running in different virtual machines or different virtual machines in different server hardware. So as you know that in the protection scenario, when we say primary and backup, the backup is always active, like both are active actually. So only thing is that the second one, the backup will be configured in such a way that it um, takes action in a different way from the primary. So that's otherwise both are active. Or even the backup is active. So the same can be implemented in different VMs as well as in the different server hardware systems. So we can achieve the redundancy in that way in case of any failure.
All right, okay. Good. Okay, so I think one last question. I know we have already taken quite a few more minutes. Can you please explain or highlight more on the physical topology of LAN and connectivity for a typical communication flow for MVSV from the individual merging unit to the VPR servers and goose messages from the VPR servers to the individual MUs?
Yeah. The first thing I'll just talk about the typical how it is happening in an 600 substation. So 600 substation, we have I mean, there are network cables that is laid for specifically for the process bus and for the station bus. So all the sample values are going through the process bus to the fiber optic um, cables preferably, and so these network cables are connected to the protection relay, and there are station bus connections happening in parallel as a separate network, and many of the implementations, the goose messaging is done through the station bus, and in many of the cases there are the goose messages, that is for the trip messages, are also connected to the process bus as well. I mean, both sample values and goose trip message are also going through the process bus. That is kind of implemented. Both implementations are available for an IEC substation. But when it comes to the virtual protection relay, this comes to I mean, there will be multiple network interface cards on an server hardware, and there will be cards dedicated to process bus and dedicated to station bus. There are PRP redundancy supported HSR PRP supported network interface cards for the process bus, and from this is made available to the multiple virtual machines in an hypervisor through different technologies. One is the virtual switch or the KVM bridge technology, and the terminology may be different in different hypervisors. And there are SRIV technology, single root IO virtualization technology, that is another way of virtualizing the network interface card to so that it is available to multiple VMs. And there is the most no, common way of directly binding the network interface card to the virtual machine. So these are different ways of connections for the process bus.
Okay, that's great. So multiple options there. That's nice. Yeah. Okay, I think that's about it. Probably if I've missed out any questions, I'll make sure that we will go through the notes and reply to you in person. Thank you so much once again for a very interactive, lot participative session. Thanks, Rupesh, for a wonderful presentation as well. Uh, as always, we'll be sharing you the presentation recording, and we'll be receiving also a certificate, an e-certificate to the attendees. Okay, thank you once again. You all have a very nice day, and yeah, thanks.
Thank you, Vinny. Thank you all.
Bye bye.